Welcome everyone to the first day of e-learning. So how this will work is I'm going to go through the lesson. There will be times where I wait for a minute or two to let you try stuff. I've got my 4 little dots here to keep it in frame. Hopefully I can manage that. And, sorry, my name is Mr. Pinta. Each day, this is how kind of lessons will go. And let's give it a try. So by now, hopefully you've downloaded the notes and you either have them on paper or you have them on your iPad and you're watching this video maybe on your phone or some way to do that. I think it's going to be very difficult to have the iPad playing the video and taking notes on Notability on your iPad. So you might want to try to figure out a way to have two things, whether it's an iPad and paper or your phone and your iPad or whatever that means. So, would everyone please, the graph below are TX parametric and TY parametric that create an XY. Label the points A, B, C, D, and E on all three. Like A is here, where must A be here and here? So let's say we're going to wait 2 minutes. Would everybody please try that? So let's look at it here. So A has a positive T and the X value is 0. So it needs a positive T and the X value is 0. So we don't really know exactly where here, so I'm going to actually work my way backwards. E here has a positive X and a positive Y. Let's see here. C has a positive Y value when T is 0. So there's a lot of different ways we could go here. So A has, I'm going to assume that the scales on these two are the same. So whatever T value is here has to have the same T value here. So this is where the A value would be here. So this must be A. So whatever the T value is here, that's a positive X. Sorry, X is 0 and Y is positive. So X is 0 and Y is positive. This must be point A. because again, it had a 0 for x, right? The vertical direction here is the output. so that must be A. So let's look at B. B is here, so that's its t-value. That looks like it's about here, so let's call this point B. So point B has a negative t-value, and negative x and y is 0. So a negative x and y is 0, that must be right here. So that's B. Point C has, that's when t is 0. So t is 0, this is point C. So t is 0, C here, so x is negative, and y is positive. So x is negative, y is positive. We don't really have an exact location, but let's put it somewhere around there. All right, and where are we up to? D. D is here, so that would be approximately here on the ty graph. So x is 0 and y is negative, so x is 0 and y is negative. This must be point D. And then we have all of them over here, A, B, C, and D. But this last one is E. E has a positive x and a negative, positive x and positive y. Positive x, so we got to live over here, and a positive y, we got to live up here. So that's somewhere over here, E, and let's call this E. And then it goes E, A, C, B, D. E, A, C, B, that was supposed to be a D there. Sorry, that's a D, we'll correct that. E, A, C, B, D. There does seem to be a pattern where we're traveling this way on this parametric. And the only one we know for sure is where C, right here, this is when t is 0. All right, so that would be the warm-up. The next section is where would you please graph each of the following? So I'm going to actually add a direction here. Would you also create, or the way we say it is, eliminate the parameter? So I'm going to give you, let's say, a minute per question. I'm going to give you 4 minutes. Would you please work on example 1 here, all 4 parts? Here are the 4 examples you just did. All 4 of them should have eliminated the parameter down to this rectangular equation, which I have dotted here. So each of them move a particle around this line differently, but they all stay on this line. So if I highlight the first one, well, as t moves, that point just moves back and forth because the bigger t is, the farther to the upper right, and the less t is, the more it moves to the lower left. And if I just play it, when it's negative, it's over there, and when it's positive, it's over there. So if I get rid of that one and put on sine, now sine just oscillates back and forth. So as when t is at one extreme of its period, it'll be big, and when it's at another extreme, it'll be small. So as I go back and forth, let me zoom in. So when t is here, it's at one extreme, and then you can see it bounces, and then it goes over here, and it bounces at the other side, and it just oscillates back and forth. If I play it, it just goes back and forth. So again, it lives on that line, but doesn't get to all of the line. If I turn that one on and turn on the exponential, so when t is big, it's way to the upper right. And as I make it smaller and smaller and smaller, it looks like it's approaching the point 0, -3, which it is. And if I zoom in, you can see it's not quite there yet. So if I make t smaller, it looks like it gets there, but I zoom in and it's not quite there. And smaller, it looks like it got there, but it's actually not. But you can see how tiny the resolution here is. Well, that means what that is representing is that these are exponential. They are asymptotic. They will never get to the value of 0, meaning this will never be 0 and that will never be 0. So we'll never actually get to the point 0, -3. So on your XY graph, you should have an open circle at the point 0, -3, and then a ray pointing in this direction, just arrows pointing to the upper right. If I turn that one off and turn this one on, there's actually no point. I could zoom out and out and out and out and nothing, because when you sub negative anything in, these are non-real values, which means it doesn't plot a point. But the second I get to 0, boop, there's the point. It just shows up there. And it actually is at that point, so that would be a closed circle with a ray. And as t gets bigger, it goes off to the right. But as you might notice, it significantly slows down because a square root flattens off. So where an exponential starts flat and then gets more vertical on both the tx and ty graph, the square root does the opposite of that. So again, this should be the whole line, this should be a segment, this one should be an open circled ray, I don't know if that is a name, and then this would be a closed circle ray. There is a key in Canvas if you want to compare your exact answer with a teacher-created key. All right, so example 2, a particle travels along the following path. So x is a quadratic, so it's going to go up and then down. Technically, it's going to go right and then left. And then y is always 7. So this is a really important moment here. If one of the two is a constant, that means it's going to travel along a straight line. We call that rectilinear motion. Rectilinear, contained by, consisting of, or moving in a straight line or lines. Whenever we do anything that we're going to consider rectilinear motion, we're going to specifically treat that linear as horizontal or vertical. Technically, on the front page, these were all rectilinear motion because they were traveling in a line once we eliminated the parameter. But for these, our rectilinear are going to be when either y equals a constant or x equals a constant. That allows us to ask a couple of new questions. So the question, for what values is t moving to the left? So what I'm going to do is I'm going to make a t, x, y table. That helps me make a graph. We want to go from -4 to 4, so I might as well do a couple of values in that range. So when t is -4, this is -7, -4, -7, that's 49, -98, so this would be -93. -4 here, well, that's just 7, and 7, and 7, and 7, and 7. So the vertex will happen at 3, 5. So I'm actually going to add 3, 5 in there. Let's sub in 0, so that'd be 9, -18, -13. And then I'm just going to go all the way to 4. If I put in 4, I get 1, -2, this would be 3. If any of those calculation mistakes are incorrect, they're at least close enough where we can get an idea of what's going on. So if I make an x, y, hold on, let me get back in the frame. If I make an xy table, then I'm going to travel along this line y equals 7. And when t is -4, I'm way over here. So t is -4, and then I'm going to travel this way, and I'm going to go all the way to when x is 5. This is when t is 3. So I'm going to travel here, and then we're going to get here, and then the y values start decreasing again, but they only decrease to 3. Well, they keep going, but technically we're only going to stay in these bounds for t. So the first question, for what values of t is the particle moving left? Well, the particle moves right from -4 to 3 for time, and then it moves left from 3 to -4. So for A, when t is 3, it's technically not moving left or right, so we shouldn't include it, and it moves left all the way up to 4. Now, whether you include that endpoint is a little bit up for opinion. I'm going to include it. So when is it moving right? B, it's moving right, again, include, and then don't include because it's not moving right or left at 3. Find the displacement. Displacement means how much has it moved from the beginning to the end. So the kind of idea there is, if I were going to run laps in PE, right? If I start here and I run a lap, my displacement is 0. So displacement is beginning to end. How how far have you left your opening spot? So we started at negative 93. Let me just double check that calculation. So that would be negative 7 squared is 49. 49, that's negative 98. Yeah, so negative 93. And we end at 3. Our displacement would be 96 units. So those are 96 apart. Find the total distance traveled. Now, distance traveled, when you do a lap, all of that counts as distance. So while we're moving right, we moved a total of 98 units. Then we moved another 2 in the opposite direction. So for D, it would be 98 plus 2, so we do 100 units of distance. So that's rectilinear motion. Pretty much it's just a parametric situation, but we can ask a couple of questions about it because since we're traveling on a line, moving right I can calculate and moving left I can calculate. Now if x were a constant, I would change these to moving up and down, but it's the same idea. All right, so do steps A through D from the previous part. So we should be getting used to these. A was create a TX and TY graph. So for A, if we make a, and I put a piece of paper here because I want more room because I want to write big enough so you can see it on camera. So this is going to be a TX graph. So that's sine. Sine looks like this. And the pi means instead of 2 pi, this is going to be 2. So this is 1. We're at 1/2 and 3/2. And then the TY graph is cosine. So that looks like this, assuming I could draw. And this is at 1. Here we're at 1/2. Here we're at 1/4. And here we're at 3/4. Okay, so there is a TX and TY graph. They would keep going, of course, but that is representative of what these are going to do. B is we talk about restrictions. So there are no restrictions on T because there aren't any said restrictions, and sine and cosine can accept any number. So there aren't any restrictions. So T is an element of the real numbers. X goes between -1 and 1. And y also goes between -1 and 1. So whenever we're creating the XY graph in part D, we can't leave -1 to 1 and -1 to 1. So we'll keep that in mind. All right, so part C, this is where we create an XY equation. Basically, the directions would be eliminate the parameter. Now, we have an issue because the inputs are different. We can't really manipulate these in a way where we could get them to be the same without a trig identity. So I'm going to use a double angle on cosine. Now there were 3 options. We had 2 cosine squared minus 1, 1 minus 2 sine squared, and cosine squared minus sine squared. Those were the 3 that we could use. Since this is sine, I'm going to use the one that has sine in it. So y becomes 1 minus 2 sine squared of half of the value that was in there before. So that's just pi t. So I can now take out sine of pi t and put in x. Y equals 1 minus 2x squared. So this is the xy graph that the particle traveling along this parametric definition has to travel on. So if I go to part D and start creating the graph, let's move it up so we're staying in frame. So if I make a TXY graph, this is XY. Now, since I know that X and Y aren't going to leave -1 to 1, I'm just going to tag those immediately so that I know that I can zoom way in on the graph, and this is all I really care about. So if I start creating a little mental table for this, it has a vertex at 0, 1, and then when it goes out 1, it goes down 2, so it would have these points. And then it would, the quadratic would keep going, so this is the function that this particle is going to move along, but it's never going to get here or here. So that's why I dotted them. It will live in here, but I'm going to wait until I start creating a TXY table to fill that in. So if I make a TXY table. Now this TXY table is going to be a little bit cumbersome. The ones with trig are always a little more cumbersome because you need a lot more values. So I'm going to go 0, and then if I go back to my graph, there's a 1/4. So I'm going to actually add 1/4 theoretically in this one. So 0, 1/4, 1/2, 3/4, and 1. And then I'll see if I want more after that. So when t is 0, x goes 0, this would be √2/2, 1, √2/2, and then back to 0. So 0, √2/2, 1, back to √2/2, and then back to 0. Where y is going to go 1, 0, -1, 0, 1. 1, 0, -1, 0, 1. So let's see what that looks like on our XY graph. So when t is 0, we're at 0, 1. So this is t equals 0. And then when t is 1/4, it moves to √2/2, 0. That's this x-intercept here, because that's when y is 0. This is t equals √2/2. And we move to it in this direction. And then when t is 1/2, we're down to 1, -1. So we get here. This is when t equals 1/2. If I were in Notability, I'd be switching back and forth in colors. I might recommend you do the same. Now, by the time I get to 3/4, I'm back to this point. So this actually goes back, and this is when, oh, that's not when t is √2/2. That's when t is 1/4 and 3/4. You can hear my dog scratching itself in the back. And then it goes this way, and then this is when we're at t equals 1 again. Now, I don't know if I ever get over here, so I'm going to go back to my table and extend it a little bit. I'm just going to throw in, I'm going to see if this happens again. So I'm going to go all the way to 3/2. At 3/2, then the x would be at -1, and the y would be at -1. So if I sub those in and evaluate, and then I'm just going to complete the full cycle for the x graph, and this goes back to, all the way back to the beginning, we're at 0, 1. So on the graph, that means that I go this way here, and this is when t is 3/2, traveling this way, and then it goes back up this way, and this is when t is 2 also. Now, we could do the plus k, where k is an element of the integers for all of these, because what's going to happen is this is going to just bounce back and forth and back and forth and back and forth. We could do it, but for today I think I'm just going to leave it as is, because that shows one full cycle of what it does. So that's question 3. You can see I made a mistake earlier. I got bound up there.